Hello physics students, let's start video 4 where we are looking at up and down motion. And in the last video we looked at dropping things, and so here's another example of a dropping question. In this case it's talking about the NASA Research Center where they research zero gravity. They have a tower that's 150 meters high and it's evacuated, so it's a vacuum, so there's no air resistance, and they can drop a 1 meter diameter sphere. And so you're given some information about this sphere in terms of its, in this case it's got an initial velocity, and you're asked for how long it will take to reach the bottom. So if you look at what you're given in the question, you're given the initial velocity, and we're saying down is negative, so that's going to be -5. It's falling 150 meters, again it's minus because it's in the downwards direction, and we're given the acceleration, which is -9.81. Now using these three, it might be tempted to actually try to use, let's see if I can do this, S equals ut plus half at squared. Now the problem with this though is that because you're actually asked for the time, you will end up with two t's. Now for those of you who do the more advanced maths, you may be able to attempt to either factorize it or use the quadratic equation. And however, I would generally recommend that you don't use the quadratic equation. So how do you get around this problem? Well, the simple solution is not to find t, but to find, let's just get this to work again, but to find v, using v squared equals u squared plus 2as. Because you have enough information here. You have the u, you have the a, and you have the s, and you do that and you come up with the final velocity. Now from there you can then find t quite simply by using v equals u plus at. Now that is a two-stage process, but you're much less likely to make a mistake doing this step rather than trying to use the quadratic equation, because generally speaking we could roughly say that about 95% of students who try to use the quadratic equation in physics end up getting it wrong. You may be a little bit different from that, or you may not be, but just recognize that this is a simple workaround. And more likely than not, the question is not only going to ask you for the time, but it's going to ask you for the velocity as well. Okay, so that's just an example of a little workaround there. Right, now throwing an object upwards. When we throw an object upwards, it is virtually it decelerates due to gravity, and then it comes back down again, and we've done the dropping objects, and so there's not much of a complication when we throw things up, straight up, instead of dropping it. It's a slight variation. There's a couple of key things to note, okay, and so basically we're looking at this as being the whole flight. So if you took a tennis ball and threw it up and then caught it at the same level, that's your going up and going down motion. And so a couple of things we like to note. Oops, where's my highlighter? Why isn't that a highlighter? Is that the velocity equals 0 at the top of flight. So that means that when it's up here, for effectively for an instant, and when we say an instant, we mean that an instant, it stops and has a velocity of 0. However, it doesn't stop there, it keeps coming down because gravity keeps acting on it. And so that's very useful, because sometimes we want to divide this flight into two sections, the going up section and the going down section, and we'll talk about that later in the next example, I think. Now the time of flight up equals the time of flight down. Okay, so it takes as long for the ball to slow down to the instant it stops, and as it does to then fall back to its starting position. Okay, and we're ignoring air resistance. Air resistance can change things a little bit, and the shape of the ball, things like that. So this is in bizarro world where everything is pure physics. The acceleration is constant even at the top of the flight when the velocity is 0. So some students think that, well, if the velocity at the top is 0, there's no acceleration. But if there was no acceleration, what causes the ball to then fall? You must have an acceleration to change a velocity. And so if the ball goes up, has a 0 velocity and no acceleration, the ball would just keep hovering there, because Newton's law says there must be a force applied and the force is equal to an acceleration. And that doesn't happen. So gravity doesn't turn itself on and off. It's always acting, and it's always pulling the ball back towards the center of the Earth. And so the acceleration remains constant. And when we do an acceleration time graph, we'll see that. The initial velocity equals the initial speed, equals the final speed. Okay, so if I throw this up at 20 meters per second, I catch it at 20 meters per second speed. The only difference being it is the final velocity equals the negative of the initial velocity. So if I throw this up at 20 meters per second up, I will catch it at 20 meters per second down. Okay, so the difference between speed and velocity there. And lastly, just a different color, air resistance is neglectable. So we're ignoring air resistance. So those 1, 2, 3, 4, 5 key points are important in our understanding of up and down motion. Alright, let's get rid of that. So here's the motion graphs that describe this up and down motion. So we're throwing a ball up and we're catching it at the same height. So x is its displacement in meters and time. So it rises up, reaches its maximum height, and comes back down. Now notice that this is a curve. It's not a straight line. Why is it a curve? Because it's accelerating or decelerating on the way up and accelerating on the way down. If you had straight lines, and a lot of students like to draw a sort of triangle shape here, it would mean that it's constant velocity, which is not the case. Remembering that a tangent to this curve gives you the instantaneous velocity. And it's not constant velocity because if we look at the velocity time graph, it leaves your hand at the maximum velocity, then slows down to the instant that it stops at the highest point, and then it speeds up in the negative direction, and so you have a negative velocity. Now this is a velocity time graph, and so that also tells us that the acceleration here, the slope is constant and the slope is equal to the acceleration, so gravity remains constant at minus 9.8, and there's no change from positive gravity to negative gravity. There's no pause where gravity turns itself off. Gravity is just constantly acting on, in this case, a tennis ball. And you really got to get your head around that, because there's a lot of misconceptions that people have about gravity or about the acceleration turning itself on and off and things like that. This is the way it is. Let's have a look at some of the equations of motion type questions that we could get from going up and going down. So in this case, there we have our ball is being thrown at 20 meters per second. We're taking g as minus 10 meters per second, and we're going to calculate how high it goes, the time it takes to reach that height, the time taken to reach the ground from the highest point, the final velocity, and the total time of flight. Alright, and so this is a very angular looking diagram of what we're showing. Here is the start, we're throwing it. Around the midpoint it's going to be minus 10 meters per second, and then it reaches 0. The acceleration is constant at minus, so it's causing it to decelerate. Up here the velocity is 0 for an instant. It then accelerates in the negative direction, getting faster and faster in the negative, and therefore it hits the ground at minus 20 meters per second. Alright, so in terms of our data, being very careful with our signs. Okay, if we looked at the whole flight, we've got U, we've got A, and we've got S. How high does it go? Okay, now for working out how high it goes, we only look at the first half of the flight, and so we can say that v equals 0 right up here at the top. And if we're only looking at half the flight, that gives us our three things, because we've got 1 and 2, and this will be our third, because the displacement doesn't help us in our equations of motion. And so we put the numbers into v squared equals u squared plus 2as, and we get, how high does it go? It goes 20 meters up. Okay, notice the careful use of the signs, and by rearranging it you get a positive displacement. The time taken to reach this height, so using that information or using just u and a and v, we can work out that it takes 2 seconds to get there. Now if you weren't careful with your signs, you would actually get a different result, or you might get a negative time, and we can't have a negative time. Next one is the time taken to reach the ground from the highest point. Well, that should be exactly the same amount of time as it went to go up, and in this case they've swapped things around, so they're working out as if the ball was dropped from here to here. So they're saying that s is minus 20, the acceleration is still minus 10, which comes minus 5, and you get 2 seconds, exactly the same. The final velocity, again they're just looking at half the flight, and so they're just working out the velocity here where u is 0 and a and t they know, and you get a negative answer. So again, careful with your signs. And then the time of flight, now what you could say is the time up equals the time down, so just add it together and you get 4 seconds. Or you can be clever and you can work it out recognizing that s is 0, you've got u and you've got a, and we put it into our equations, solve for t, and you get 4 seconds. So you can do it mathematically or you can do logically. Alright, so the next video is all about recapping what we know about vectors and scalars and components. Cheerio!